So lighting a multi-billion-dollar metallurgical asset is the most high-stack event in anyone's blast furnace career. So you are essentially lighting a match inside a vessel designed to last more than 15 years, and to do this successfully, we rely on a precise engineering based known as a timbering. So by end of this technical session, you will master the three core deliverables. First will be the structural matrix required to support a 100% coke blank. Second is the geometric logic of the log cabin pattern, and the third is about a ignition bridge required to transition from a cold state to 2000 degrees centigrade, and all the three are equally important, so we cannot say that this is more important than others. So look at the blueprint on your screen. So notice the orange glow in the crucible. That is our engineered timber stack. On the left, we see a structural matrix, crucible depth of 2500 mm and expansion tolerance of plus or minus 5 mm. Here is about asset longevity. So failing to hit these parameters means risking parameter are very prone to premature refractory failures. So before you first cast, so these things may occur. So to understand the why, we must first see where timbering fits into the broader commissioning timeline. So coming to our next slide, which is about this timbering in the commissioning sequence. So we can see the flow chart from left to right. We begin with the refractory drive, control moisture removal up to 800 degrees centigrade to prevent steam explosion, and then comes cooling and inspection where all systems are pressure tested. Notice the highlighted third block, which is about the hearth wood feeling. So this is the critical transition before coke blank, charging and ignite. So many engineers ask why we enter a cold furnace to stack wood. So this is a really matter of a great curiosity. So the operational impact is a reduction in thermal shock. So by placing this combustible scaffold in the crucible, we ensure the furnace doesn't just jump from ambient to extreme temperature. Instead, we create a controlled ramp up. If you skip the cooling and inspection gate, you risk introducing combustible material into the leaking vessel, and uh, which is a recipe for the catastrophe. So we must respect this linear logic to ensure a safe long-term campaign. So with the sequence established, so let's analyze the three strategic engineering pillars of the scaffold itself. So coming to our third slide, which is about the strategic engineering. So we can see that look at these three icons in the center of the side. On the left, the weight and the spring icon represent mechanical protection. So the timber acts as a physical shock absorber for the brittle refractory pad, protecting it from the high velocity impact of the multi-ton initial coke blank. The center icon showing gas eddies represent high porosity gas routing. We are creating a calculated high voidage zone at the lowest point of the furnace to ensure initial gases produced at the tuyer can escape through the taphole without pressure buildup. So finally, on the right, the flame icon represents the low temperature ignition breeze, and this bridges the thermal gap between the hot blast and the high ignition threshold column. So the factor here is simple. Without this scaffold, your furnace would likely rather suffer from the localized hard chilling or dangerous pressure excursion during the first 24 hours of operation. And achieving these objectives require very specific combustible material, which we examine next. So technical specification for combustible material is our heading for this section, where we observe the material hierarchy required for a successful blow-in. First, we have a structural timber sleepers, large dense wood logs that serve as the primary load-bearing scaffold, and these must support the weight of the 25 to 40% working volume oak plank without premature collapse. Second is looking at the light kindling and shaving. These have a high surface area to mass ratio for the rapid flame propagation. And third, notice the oil drop icon representing hydrocarbon saturation. This is the most delicate action, applying oil to the kindling to lower the ignition threshold to the absolute minimum. The operational impact of this ignition catalyst is the guarantee of immediate lighting upon the introduction of first hot blast. So if you lack proper saturation, you risk symmetrical ignition. So where one side of the furnace stays cold while the other melt, leading to a massive thermodynamic instability. So these materials are only as effective as geometry in which they are stacked. So structural geometry of the log cabin pattern. So if you see, observe the isometric 3D model on the right. So this is the log cabin pattern. Point 1 shows the 90-degree alternation. So each layer of the sleeper is placed perpendicular to the one below, creating a self-supporting interlocking matrix. Coming to the point number 2, which highlight the load bearing capacity. This leads design safety transfer, mechanical loads always from localized point on the refractory. And finally, look at the point 3, the center void. So these overlapping structure inherently create interconnected vertical and horizontal channels. So this is the secret sauce of the blow in. The wood refuses to compress into a solid impermeable mass under pressure. So factor is the force permeability. So even under the crushing weight of the burden, these channels stay open, allowing your blast energy to reach the center of the hearth, preventing a dead man from the forming before the campaign even burns. So these geometries specifically designed to manage the path of least least resistance rather. So now let's coming to our next slide, which is also very important about porosity logic and initial gas permeation. So look at the cross sectional diagram. The orange arrows indicate the path of least resistance when the furnace is first lit. The massive coke column above act as a dense plug. Therefore, the early combustion gases must move downward. Follow the arrow as they move through the timbering gap, through the crucible, and finally out there, um, um, uh, out through the exhaust routing at the tap hole. So the voiders engineering ensure that the expanding gases are directly safely to the open tap holes. So if you fail to maintain this porosity logic, the gas will channel up to the wall, causing a localized overheating and dangerous pressure spike. So this is about thermodynamic safety. So we are the engineering a path for the furnaces to breathe while it's still too cold to establish its normal upward flow. So to ensure these gas and eventually slack can actually leave the vessel, we must manage tap hole integrity. And our next slide, which is about a tap hole integrity and exit channel management. So on the right, notice the glowing orange pipe leveled as the iron notch. So this is a strategic placement. We place wooden sleepers or specifically sized hollow wooden pipe directly at the internal opening of the notches. So as the furnace transition from producing gas to producing initial liquid slag, so these wooden insert ensure a physical channel remaining completely on obstructed. This is channel preservation. So this first accumulation of slag is often silica and alumina rich, making it increasingly or incredibly viscous. So here is the slag drainage. Now if you don't have a clear path to exit, the liquid will accumulate and freeze, causing a hard freeze up within the first 24 hours. So we are essentially pre-drilling our exit route with organic material that will burn away exactly when we need the liquid to flow. So yeah, now that we understand this logic, that let's look at the specific layer arrangement used to build this scaffold. So coming to the volumetric parameters and the layer arrangement, so observe the structural layer matrix for a large capacity furnace. Over 3000 cubic meter, we require approximately 200 cubic meters of wood. So look at the four packages type. The closed packages at the bottom create a solid floor. The one space, space and three space packages use gap equal to 1, 2 or 3 sleeper width respectively. So notice how the gap increases as we move up the 39 layer scaffold. So this is mm, intentional, and we are maximizing voidage near the center axis to facilitate the vertical gas flow. The operational impact of this tiered arrangement is a balanced thermal profile. By varying the package's density, we control exactly where the heart of the fire will be strongest. So if you use only closed packages, the gas would be trapped. If you use only three space, the stack would collapse under the coke load. So the final piece of this combustion puzzle is the interference, where the blast actually enters the furnace. So combustible interface at the tuer elevation. So looking at the blowpipe and the tuer cross section on the right, notice the ignition catalyst. The right kindling and wood shaving packed directly in front of the tuer opening. So these localized zones receive the highest concentration of the oil saturation to lower the ignition threshold. So the target alignment node is critical. These materials are built up to align perfectly with the horizontal plane of the tuers. So this ensures that whether you initiate the blow in with red hot iron bars or a low volume hot blast, the reaction is instantaneous. So delayed ignition at the tuer leads to gas buildup in the dust catcher and the gas cleaning system, which can result in a dangerous explosion. We pack these tuers with oil soaked oil to guarantee that second the oxygen hit, we have the fire. So with our engineering plan in place, we move into the execution phase, starting with foundation. So coming to the execution protocol, phase 1, so preparation, and which is about a preparation and foundation. So this is our phase 1 flow sheet. Step 1 is the dry out debris clearance. So we must see bare refractory before we begin. Step 2 is the cooling system audit. This is a critical gate. Zero moisture leakage is permitted. If a step is leaking here, you must replace it before proceeding, or you risk hydrogen explosion later. Step 3 is the taphole seeding, where we position our exit pipes. Finally, step 4 is the base scaffold layering, where we place the closed packages, sleepers directly onto the hearth floor. The so here is the foundational integrity. If your base scaffold is uneven or your hearth floor is covered in a dry out ash, the entire 39 layer stack could shift our tilt, causing a symmetrical gas flow that will plague first week of your operation. So once the foundation is level, we begin the vertical build to the top of the hearth. So, coming to our executional protocol, which for the phase 2, we can see that the vertical build and the charging steps in particular. So step 5 continues the build with the remaining 38 layer. We strictly follow the space packages blueprint to the maintain that center void. So step 6 is the tier interface packing, which we just discussed. So step 7 is the personal evacuation and the sealing. And notice the detail. We pack inactive tiers with the clay balls to ensure proper blast velocity through the active ones. And finally is the step 8. The step 8 is the cook blank charging. So dropping the initial 100% cook burden from the top. So the operational impact here is the structural validation. So the timber scaffold must now bear the entire mechanical load of the coke column. So if the log cabin geometry was executed correctly, the scaffold holds firm. If not, the wood crushes prematurely and you lose your porosity before the first match is even lit. So now all your engineering culminates into the moment the reactor is activated. So now coming to our one of the most valuable slides on transition to the ignition, and which is about activating the reactor. So on the left is the static state, wood and coke ready to react. On the right, the active reactor, that is, notice the orange flame bursting from the tuyeres and the molten liquid beginning to exit the taphole. So we allow the wood to burn under the natural trot for 24 to 36 hours before introducing the blast. So the wood scaffold safely burn away, leaving a preheated, mechanically intact hearth pad. And this is ultimate blow in the milestone, achieving a continuous flow of liquid iron and slag without a freezer. So by following this hearth timbering protocol, you have engineered a path for the success. So you are no longer just lighting a fire, you are stabilizing a mammoth, this vessel, the reactor, the blast furnace.